I'm Saharon Rosset. I'm from Tel Aviv University, Israel. I'm a statistician, and this is going to be hopefully a super lightweight talk, just like general interest talk about some examples of the importance of combining rigorous formulations and rigorous results in thinking about data, and properly choosing between the different models so that we reach conclusions that are actually valid and useful. So that's kind of the general theme of what I'm going to be talking about. And I found a really nice XKCD comic that says that out of the people who actually know the statistic that only 1 in 7 million people die from lightning, the actual death rate is 1 in 6, because these are the people who are always running out in bad weather. So this is really about conditional probability, and most of what we're going to be talking about is about conditional probabilities and taking into account the relevant conditioning and doing it correctly. Okay, so as I said, our goal is to revisit some elementary topics. I do it in 2 halves. The first half will be about probability and very elementary. Just remind ourselves some properties of conditional distributions that we know, and connections between different types of conditional distributions. And Simpson's paradox, to me, is a very good demonstration of the fact that we need to spend time thinking about what conditional distributions mean, and what additional conditioning means, and what's the right level of conditioning for the conclusions that are appropriate and relevant to the data we are looking at. So that's going to be the probability part. And then for statistics, we'll talk about interpreting simple linear regression results. Again, a very elementary topic. And I'll show a real-life example where we know what the rules are, but it turns out that it's not always completely obvious how to apply the rules. And then we need to ask ourselves whether it's really not clear what's going on, or whether there's a correct way and an incorrect way of applying the sort of the mathematical basic formulations, and what it says about what are the correct conclusions and incorrect conclusions from the data we're looking at. Okay. So just a quick reminder of things we all know. Bayes' law basically says that if I want to know something about the conditional distribution one way, I can base it on the conditional distribution of y given x. I can base it on the conditional distribution of x given y with these adjustment factors of the marginal distributions, just applying the definition of conditional distribution or conditional probability twice. The law of total probability means if I want the probability of some marginal event, some value for x, I can get it by summing over values of y, the joint distribution of x and y, the joint probability of x and y, so that's this equality. And then I can apply the definition of conditional distribution and get the sum of the conditional of x over y, condition on y times the marginal of y. And what I noticed that what I have here is just the denominator of the first one, and that gives us the famous, if you want, Bayesian posterior inference formula, or just a very useful formula in general. If I want to know the probability that y takes a specific value given x, I can express it as the sort of conditioning the other way times the marginal, divided by the sum over y of all values on the numerator. And so just a few formulas that we have to keep in mind whenever we think about conditional distributions. Okay, so this is all very trivial. And the point is that if I know only about the conditional of x given y and the marginal of y, I can make inferences about the conditional of y over x. So here we start with something that I think is really trivial. I hope everybody here knows it, but let's just do a sanity check. So Eleazar was telling us about his wonderful COVID tests last year. So he's now advertising that his tests are extremely accurate. And what he means by that is that 99% of the people who are actually carriers get a positive test, and 99% of the people who are non-carriers or are healthy get a negative test. So that's a 99% accurate test, which is very good. Now I get tested and I get a positive result. So, you know, what's the precision? What's the positive predictive value? What's the probability that I'm actually a carrier, given that I got a positive result in the test? And again, we're not going to waste time asking the audience, because I'm sure that many people here know, or most of you, if the disease is rare, then that probability of being actually sick, given that I got a positive test, can be actually very low, even though the test is 99% accurate in both of these sort of apparently exhaustive terms. Okay, so let's do a calculation with our formulas. So we define these two binary variables. Y is whether you're sick or not, and X is whether you got a positive test or not. And what we're given is that X given Y. So given that Y is some value, the probability is X is the same value as 0.99. This is right, what we said about the test being 99% accurate. These were statements about the conditional distribution of X given Y. We also we also told that the marginal probability of Y being 1 is 1 in 1,000. All we have to do is plug it into our formulas. Yeah, basically I plugged it into the last formula. We could use other formulas and get that the probability, the positive predictive value of this test is less than 10%. Okay, so again, pretty trivial, but it's hinting us at the fact that when you think about conditioning on different things, your results can change their meaning, or can have the conditioning on different things can lead to very different results. Okay, so this is trivial. Simpson's paradox. Hopefully, most of the audience has heard of Simpson's paradox. It's maybe a bit less trivial, but still pretty trivial. So now let's assume we have 3 binary random variables. Y, which is our variable of interest, say whether someone is sick or healthy. In my example, actually, it's going to be whether someone dies or doesn't die. So that's a pretty important response variable. And then we have 2 other binary variables, X and Z. And there's 2 conditional distributions we can think about when we look at data. So we might think about the conditional distribution conditioning only on Z, or we might think about the conditional distribution conditioning on both X and Z. And the point of Simpson's paradox is that there can be very different conclusions when you condition on different things. And let's say that we are primarily interested in the effect that Z has on Y. So Z is our variable, sort of the thing that we are interested in. And we want to know whether Y is more likely under one value of Z versus the other. That's our sort of our fundamental question, is whether Y is more likely to happen under one value of Z versus a different value of Z. And the paradox, which is really not a paradox, it says that it's possible that if I condition only on Z, then Z1 would make Y equal 1 more likely than Z2. But for every single value of X, if I condition both on Z and X, then the combination of having Z1 and X would make Y less likely than the combination of having Z2 of X. Okay, so the first row is saying if I just ask about the value of Z, then Z1 makes Y much more likely than Z, or more likely than Z2. And the second line says, for every single value of X, if I ask, given that I have this value of X, which value of z makes y more likely, then for every single value of x, in this case only 2 values, then z2 would make y more likely than z1. So this is, it seems maybe absurd at first glance, but it's not absurd, and it's very possible. But beyond the fact that we need to convince ourselves that it's possible, we really need to ask the question now, as people who care about conclusions that are in some sense actionable or relevant to the world, is the conclusion from that z1 makes y more likely or z2 makes y more likely? And yeah, so I want to say that before we answer, or before we show how it's possible, that's like, it's a good question, because the general answer is that it depends, like many things in life, and it depends on what the correct level of conditioning is for the specific conclusion that we want to draw. And in the two examples I'm going to show you, we could argue that in one of them, the correct level of conditioning is conditioning on 2 variables, and in the other one, in some sense, the correct level of conditioning is conditioning only 1 variable. And so you should condition on the correct things to get conclusions that are really useful and relevant for your purpose. So let's just see, first of all, the general mathematical reason why this is possible. The key is that the probability conditioned on 1 variable is a weighted average of the probabilities conditioned on 2 variables, and the weighting are these marginal conditionals. So they are the conditional of x on z. And these can behave in ways that affect the change between the conclusions when we move between levels. So let's just see an example. It's a bit outdated, but I heard some COVID stories here, so maybe not that outdated. But it was a big deal at the beginning of COVID, how people were dying extensively in Italy and not dying so much in Germany. So we have 2 countries, we call them Italy and Germany. And the fact that we hear on the news is that in Italy, patients are dying at a much higher rate than in Germany. So everything we do now is conditioned on being infected with COVID. The entire population we're interested in, being infected with COVID is not one of our variables. The entire population we're interested in are people infected with COVID. Our variables are, okay, I'll define the variables rigorously in a while. But we observe then that the mortality rate is much higher or higher in Italy than in Germany. But when we look at young patients, we see actually, it's hypothetical, but it's possible. When we look at young patients, we see that the mortality rate among young patients is higher in Germany than in Italy. And when we look at older patients, we see the mortality rate among older patients is higher in Germany than in Italy. Okay, so within age groups, people are dying more in Germany. Overall, people are dying more in Italy. So I hope you see that this is exactly the type of conditioning situation that we discussed, right? We'll make y whether you live or die, z your country, and x whether you're young or old. Of course, everything can be continuous, but for simplicity, the variables are binary at this point. And the statements we've made are that the probability of dying given that you're Italian is bigger than the probability of dying given you're German, and that the probability of dying given you're Italian and young is smaller than the probability of dying given you're German and young, and similarly for old people. The probability of dying given you're Italian and old is smaller than the probability of dying given you're German and old, right? And I think for this example, it's pretty easy to see what would cause this phenomenon. The fact that young people get sick in Germany and old people get sick in Italy, right? So if you have, if most of the patients in Italy are old, and we know that the death rate among old is higher, and most of the patients in Germany are young, there's no contradiction at all in any of these statements. And so, okay. I don't have the question here, but the question now remains, do you want to live in Germany or do you want to live in Italy? Yeah, and the answer really depends on whether you're interested on what happens to you conditional on getting infected or not conditional on getting infected. There's another condition in question. In general, yeah, I don't know what the answer is. It's going to be clearer. The correct level of conditioning is going, I think, to be clearer in the next example. So, so far we talked about the simplest case where you just think about conditional probabilities. It gets a bit more interesting and challenging when we try to think about conditional expectations. Of course, conditional probability is an expectation of an indicator variable, so in some sense, the expectation case covers the probability case as well, but let's think about expectations of specific quantities of interest, and a quantity of wide interest is money. So let's think about expected income as our response now, and this is a true story. Around 2011, there was a national debate in Israel, much smaller than the national debate going on right now, but still there was many people who cared about this. How should the taxation work on the natural gas, the big natural gas deposits that were discovered? So how should the companies be taxed for when they extract and sell the gas? It's of course, at that point, we were talking about future profits. The gas reservoirs have not yet been developed even, but we knew they were there. And so there was a very interesting claim from the gas companies. And the gas companies said, if the tax will be too high, we are not going to be able to get the bank loans to develop the gas wells, and the state will lose money if it makes the tax high. Okay, so that was, whether or not it's correct, that was the claim by the gas companies. So let's look at that as an example of Simpson's paradox. So Y would be the profit, the money that the state makes. X would be whether the tax is high or low. So Y is continuous, X and Z are binary. X is whether the tax is high or low, and Z is the loan status, whether or not they manage to get a loan that they need to develop for the initial investment to develop the resource. And what they are claiming is that the expected value of Y given that X is high is smaller than the expected value of Y given that X is low, right? So the state will make less money if it puts a high tax than if it puts a low tax. So this is their claim. And we also know in this case from first principles that if I make the tax high, I generally make more money than if I make the tax low, right, as the state. So specifically, if I make the tax high and they manage to develop their resource, I'm going to make more money than if I make the tax low and they manage to develop. And if the same happens if they don't manage to develop, maybe it's equal to 0 if they don't manage to develop, but it's not lower. There's no way the state income would be lower than if the tax is high than if the tax is low. Okay, so this is, as we see, another example of this phenomenon. And this we can explain, I think, we can explain their claim. I'm not saying it's correct, but we can explain their claim pretty clearly in terms of conditional probabilities. Again, it's that phenomenon. What they're saying is that the probability that we manage to get the loan if you make the tax high is much lower than the probability that we manage to get the loan if the tax is low. Right? So when we go and weigh these quantities, these 4 quantities in the second set of inequalities, the 2 quantities at the top are weighted average or weighted means of the 4 quantities at the bottom, and this saying that the weight functions can be such that all of this will hold. This may or may not be a reasonable argument, but it's mathematically possible what they're saying. And I think in this case, it's pretty clear that if they are correct in their statement, then actually they have the right level of conditioning in mind. Because now the state has to make a decision about tax, so it really cares about what happens conditioned only on tax, and not the entire detailed chain of events, so getting the loan or not getting the loan and so on. So this is an example where the right level of conditioning seems obvious, and it seems to be the less detailed level of conditioning. If anyone, I'm not going to get into it, but if anyone knows the classic Berkeley acceptance rate Simpson's paradox example, there, when you think about it, it's clear that the more detailed level, conditioning on more things, is a more valid way of drawing conclusions. So, okay. So this is the part about probabilistic thinking. And one point I wanted to make sure I make is that conditional distributions are critical for interpretation, and they may not be the most intuitive, but specifically, which direction and which level of conditioning is relevant to our specific problem is something that we should be careful to think about carefully. And I think something that at least I would like to emphasize is this idea that it's extremely useful to move between just intuitive discussions about data in the world and rigorous, clear mathematical statements about distributions, and in particular about conditional distributions and different levels of conditioning. So, so once we express things in terms of conditional distributions, we have all these laws of probability that can help us to be more careful and accurate about the conclusions we draw. So that's it about probability. If there's questions on this part. Okay. So the second half of my talk is going to be about linear regression. And in a similar spirit, we're trying to bridge the gap between sort of mathematical formulations that hopefully all of us know and intuitive conclusions, in particular correct intuitive conclusions when we look at data. Now we're going to fit a simple linear regression, univariate linear regression of y on x. And we are asking ourselves, how strong is the relationship between x and y? And we have different ways of measuring the strength of the relationship. One of them, by the way, is the t-test p-value. I'm not going to talk about that at all because that's not actually a measure of the strength of the relationship. That's a measure of the significance of the relationship, and we're not interested in that. We live in a world where we can assume a relationship exists, and we just want to know how strong the relationship is, and that's our problem of interest. So an obvious first measure is the regression coefficient of y on x, right? And this is a well-known formula for the regression coefficient. Another option is to take the correlation between y and x. And so the correlation, what is it? It's the empirical covariance on the top divided by the product of the empirical standard deviations at the bottom. And with not much math, we can conclude that it's attained by a simple transformation of the regression coefficient, the transformation of multiplying by the ratio of the empirical standard deviations. Okay, so we have a clear relationship between these two. And a very important quantity is the percent of variance explained by the regression, often denoted R square. And this rho is often denoted R, and it's not surprising to find that R square is equal to R square. That's actually not a very trivial mathematical identity, but hopefully most of us know it, remember it from regression class. So that means that the R square, the percent of variance, the percent of the variance of y that's explained by its regression on x is equal to that transformation on the right of the slope. So we have the slope of the linear regression multiplied by that ratio, and here squared. So these are possible measures of the strength of the linear relationship, how useful X is in predicting Y. And one question we might ask ourselves is which of these should be used to quantify how strong the linear relationship is, and why should one be used versus the other? And the key property, which I think is very important, is the notion of being sensitive to the scale of at which X and Y are measured. So scale, when I say scale, what I mean is standard deviation, right? Not the centering, but the standard deviation. And the obvious example is if I take X, say X is measuring some distance, and now instead of measuring it in kilometers, I measure it in centimeters. So I multiply each value of X by 10 to the power of 5. What happens to my measures of strength of a linear relationship? So what I know will happen is that the linear regression coefficient will get divided by the same factor, by 100,000, and that the empirical correlation and variance explained will be unchanged. Right? So in that sense, and the key to that is this. If we just want to think about the formulas, the key to that is that relationship that basically makes the quantity on the right, on the left scale independent versus the quantity on the right that doesn't take into account properly the scales, or that's not the job of the slope. So it doesn't take into account the scales. So if we agree that by changing the units of measurement, the strength of the linear relationship hasn't changed, if we all agree on that, then we know that we should not be using the slope as a measure of the strength of the relationship. We should be using rho or r squared. What's the main problem with using the correlation as the strength of the relationship? Anybody can tell me? Sign, exactly. So going up and going down means different things when we look at correlation, and they mean the same when we look at the percentage variance explained. So actually which one we choose, and also the scales at which they work. So, but they both share this property of being invariant. By the way, the correlation is invariant to linear transformations with positive coefficient, and the percent of variance explained is invariant to both signs. Okay, so this is very, very obvious. And maybe we can try and see if it's as obvious when we go and look at data, what's the right thing to do to evaluate the strength of the relationship. So we're going to go back to the 19th century, early 20th century. And there's very famous work, basically by Galton and then Pearson and Lee, all of them famous people, followed up on it. And the point is that if you regress a child's height on the parent's heights, father or mother or the average, then you get coefficients that are positive but far from 1, so between 0.5 and 0.7, depending what you do exactly. And Galton called it regression to the mean because, or the less politically correct name, regression to mediocrity, because if the parent is very tall, then the child will be tall, but not as tall as the parent. And if the parent is very short, then the child will be short, but not as short as the parent. There's a famous story about that in the Israeli Air Force, that they were each week choosing to denote who the best performing pilot was. And they noticed that the guys who get selected for being the best performance always perform worse the next week. And so they were very distracted by the fact that the prizes are reaching the opposite goal of what they are supposed to, but in fact they were just observing regression to the mean. Okay, so here's some data from Pearson and Lee This is taken from the paper from 2013 by Pagano and Anoke, but it's actually data from the 1903 collection by Pearson and Lee. And this is looking at the regression of a child's height on the mother's height and the father's height. And what I want to show you is the red versus blue. So I don't know how much, you can probably see it from the back. So if I just regress the son's height on the father's height, I get a coefficient of 0.516. If I regress it on the mother's height, I get 560. So this is the red versus the blue at the top. Then if I do a joint regression, I get a similar phenomenon that the mother's coefficient is bigger. And if I do the daughters on the parents, I get the same effect. For univariate regression, the mother coefficient is bigger. And at the bottom for bivariate regression, also the mother's coefficient is bigger. So we have a consistent phenomenon that when I regress children's height on their parents' height, I get bigger coefficient for the mother than from the father. So this is kind of suspicious and maybe worrisome. And we have to ask ourselves, what could be reasons, or what should be the correct reason for the fact that we're getting different coefficients for the mother and for the father. So here's an explanation one that I actually don't know who proposed it, but I saw it attributed to some people, but I don't believe that anybody actually made this proposal. But so here's a proposal. Fathers are taller on average. So the smaller coefficient is to somehow equalize the contribution of the father and the mother because fathers are taller than mothers. And why is this argument completely incorrect? What do we do when we calculate the slope of the regression? We subtract the mean, right? So the mean has no effect whatsoever on the slope that we're estimating. That's obvious from what linear regression should mean, and it's also obvious from the mathematical formulas. So we know that there's no way this is correct. This is a correct explanation. The second explanation is actually the title of the Pagano and Anoke paper. And the title, so also in my title I have mommy and daddy, just to be consistent. So why are mommy's coefficients bigger than daddy's? So they say maybe an explanation is mommy's baby, daddy's maybe. Okay? And that also already tells the story of their hypothesized theory. So their hypothesized theory is that there's no non-paternity. Okay, and it's actually, we won't go into the math, but it's actually pretty simple to ask the question, how much non-paternity? So when there's non-paternity, it basically says I have a random man designated and a random daddy who's not the actual daddy, so there's zero correlation between the daddy and the child. So there's some percent of daddies who are not daddies and give zero. And there's the other majority who are actually the daddy. And once we take that into account, we're going to equalize the coefficients. Okay, and you can do that calculation. It's not complicated. And once they do that calculation, they conclude that between 4 and 7% non-paternity. So it can be estimated based on boys, girls, univariate regression, bivariate. You get slightly different numbers, but you get between 4% and 7% non-paternity in the data. So that's a pretty far-reaching conclusion. And that issue of non-paternity has been a hot issue in research for many years, and it's been attacked in different ways. And they, according to their claim, they have strong evidence here of non-paternity, of a substantial percent of non-paternity in this data. Collected at the end of the 19th century. This is high data from the 19th century. And so now we may ask ourselves, is this explanation consistent with what we just said about linear regression influence measures? And is there a different explanation that can be applied here? Okay, so I'm going to open this if anyone wants to give an idea why this may or may not be the right way to think about the linear regression. Yeah?
I don't know if this really answers your question, but is the standard deviation of one of the set of heights different from the other set of heights?
I haven't told you anything about that, but definitely a good question to ask yourself. So is there an answer to that that could explain the discrepancy? Okay, so yeah, I mean, you're exactly right, so let's see it. Before we get to that point, let's go with what we said. We just said that you should look at the correlation coefficient as something that's insensitive to scale rather than at the regression slope as something that is sensitive to scale. And when we look at the correlation coefficients, this is from their paper, right? So I want to emphasize that this appears in the paper, Mommy's Baby, Daddy's Maybe. And it's actually also taken from the 1903 paper. But all of these statistics are taken from the 1903 paper. And these are not the correlation coefficients of the boy with the father, boy with the mother, girl with the father, girl with the mother. What do we see in the correlation coefficients? We see that the correlation coefficients are actually slightly bigger with the father's height than with the mother's height. Okay? So do they tell the same non-paternity story? They don't tell the same non-paternity story, but which of these stories should we rely on, and how can this discrepancy be explained? So we get exactly to Joe's point, that Daddy is back in the game, and the key to Daddy being back in the game is this observation that the empirical standard deviation of father's heights is about 15% bigger than the empirical standard deviation of mother's heights. And this is something we know in general, that men's heights have more variance than women's heights. Okay, so the combination of having higher standard deviation, having higher standard deviation is like moving from measuring in kilometers to measuring in centimeters, right? I mean, this is much less extreme example, but it's the same phenomenon, that having different standard deviation is having different units of measure for the heights of men and women. So our first conclusion is that from this is that the variance explained of the father's height is no lower than the mother's height. We know that because the correlation is no lower, and the variance explained is the square root of the correlation. And the more important conclusion is that there's actually no evidence of non-paternity in this data, and there might be slight, probably insignificant. We can see the standard deviations on these, the estimated standard deviations here, and conclude that it's not really, because it's not significant, but actually if there's any direction that the data is leaning, is a stronger effect of the father than the mother, and not the other way around. So anyway, our honor as men is saved at the end of this analysis. Okay, so I didn't take my entire time, but that's it. Thank you.